Hello everyone. I am Dilip Tabe and my teammates are Mokshan Kolmadi and Isita Dinujay. Today, we will present to you a brief introduction about quantum communications, including its evolution, how it works, and what its future looks like. Quantum communication is often seen as the next big step in telecommunication. Instead of using bits and other normal signals, we transmit qubits encoded in photons using quantum mechanical principles. This allows us to do things that were fundamentally impossible using classical methods. Some key principles behind this are the no cloning theorem, the BB84 and E91 protocols, and Bell's inequalities. But the idea of quantum communication isn't new. In fact, in 1935, Einstein, Podolsky, and Rosen questioned whether quantum mechanics were complete or not, and these doubts helped to lay the foundation of modern quantum technology. Then, in the 1970s, Stephen Wiesner introduced the idea of conjugate coding and laid the groundwork for quantum cryptography. In 1991, Carter Eckert proposed the E91 protocol using quantum entanglement for quantum key distribution, and in 1992, a year later, experiments confirmed that keys could be exchanged securely over optical channels. Then, in 1997, Anton Zeilinger's team achieved the first successful demonstration of quantum teleportation and transferred a quantum state via entanglement. Also, in 1998, the concept of quantum repeaters was introduced, which would enable communication over longer distances. Now, I'll hand over to Isita to guide you through the mechanics of this technology.
When it comes to the quantum communications, the first thing that you have to identify is what is qubit. Now we know in classical communications a bit is a 0 and 1. In quantum communications a qubit has 0, 1 and both 0 and 1 superimposed at the same time. So we can transmit that qubit through the quantum channel. The second thing that we need to identify is that okay, we can transmit, but is it secure? And there comes the non-cloning theorem. And through non-cloning theorem, what it states that is, it says you can't duplicate or clone a qubit if you don't know it. And this is the foundation for quantum key distributions. And the third thing that we need to identify, okay, we can transmit and it is secure, but we need protocols, right? And as a result comes the BB84 protocol. And furthermore, what we can see is that if someone tries to hack our information, then our quantum state gets disturbed and a receiver can identify whether someone attempted to get our information through that disturbance. And the last thing is the quantum repeaters and quantum memories. Now, a quantum repeater uses when you try to communicate through long distances. You can divide that into shorter paths and put quantum repeaters in behind. So quantum memory catches the qubit, it entangles the quantum state through a quantum repeater and then retransmit. Through this, we can transmit through long distances. Now I hand over Mokshan to talk about the concerns and future trends.
Quantum communication has a lot of promise, but there are still some big challenges, especially when we try to make it work on a large scale. For example, it can be hard to keep everything in sync. There is a lot of extra work, need to fix errors, and signals can interfere with each other, especially when we send both quantum and regular data through the same fiber cable. Quantum signals are also very delicate. Things like changes in temperature or nearby electrical signals can mess them up. This can break the special quantum properties like superposition and entanglement, which are key to making quantum communication work. Still, the future looks exciting. Experts think the quantum internet market could grow to $8.1 billion by 2030. That's pushing companies in telecom, cloud computing, and cybersecurity to work together and develop this new technology. These also progress in space. China wants to launch more quantum satellites by 2025, and Boeing plans to put one in orbit by 2026 to connect quantum computers around the globe. So, we have looked at how quantum communication has grown, how it works, the problems it faces, and what's coming next. There's still so much more to discover in this field. It's not just a dream for a future. We are building it today. Thank you.